Next up, going back into the academia standpoint, one of the things that I get excited about from that education standpoint is as we've heard, there's a lot happening in this industry. So it's really important to highlight the work that the next future and the generation is going to be doing for this. That's why I'm excited to welcome up Adam Williams, who is a PhD student at the University of Minnesota. And his research is really primarily focused on the development of soils in off-Earth environments. He's been a big advocate and fan of the conference for years. So Adam, it's good to have you up on the virtual stage here.
Here, and I'm happy to have the opportunity to not just attend, but share some of my work here with you. So we can go ahead and get started. So as Andrew said, my work is primarily around the transformation of regolith into soils. We may see some overlap here with some of the other presenters, but I think that's just because great minds think alike. So a little bit about me first. I'm a professional engineer for my day job. I have a background in research and development and test and quality control. And my educational background, I have a BA in economics and philosophy, a master's in software engineering, master's in biomedical informatics and computational biology, a graduate certificate in space resources. I'll be getting my third master's here in just a few weeks in space resources, and am a PhD student hoping to graduate in the next year or two. My research goals are really around the development to transform lunar regoliths into soils and to really understand and characterize to support off-Earth agriculture. And it's broken down into several areas: the biological, the chemical, the physical, and the structural changes needed to really enable space ag. When we look at the current space landscape, we have the Moon to Mars mission, and we see with less than a decade, we hope to have a permanent settlement on the Moon. So we have the US-led Artemis Accords, but we have competing national efforts, whether from the Russia and China, as well as other third-party countries. And we also have private enterprise through SpaceX, Blue Origin, ULA, and these other startups. And there's a very serious demand, as I think most people at the conference see, for geology and environmental systems and regenerative systems that take advantage of space resources. But there is an interconnection as well to improving our situation here on Earth. And so when I look at this situation, I see one problem, a critical problem, and I think Senator Hoeven alluded to it as well, is that without food, we're not going anywhere, right? We've heard of the tyranny of the rocket equation. The further we want to go, the more fuel we need to bring. Humans are like chemical rockets. The further we want to go, the more food we need to bring, and therefore the more fuel we need, and the tyranny just takes over. The average astronaut eats about 4 pounds of food a day, and when you run the numbers, if we launched every rocket in 2020 to support food for humans on the Moon, we could maybe get 100 people, really 80, 81 people, something like that. And realistically, we can support maybe 14 people by my calculations. And astronauts don't just need food, they need medicine, they need entertainment. We're biologically co-evolved with plants. So you speak to astronauts and they talk about being fascinated with grass when they come back, things like that. So we really need to be able to sustain people out there. We're going to need to bring life with us. So my approach, as others here, is to solve this problem, and maybe a little different, is to use lunar resources and live off the land, transforming the supply lines. Well, I think hydroponics and other technologies will be really invaluable to get going. When we want to really expand human settlement and go further beyond to Mars and elsewhere, we're going to need to be able to live off the land. And I don't just want 10 people in space. I want millions, if not billions, of people out there. So this is really key from how I see it. And I think we can do this leveraging regenerative agriculture. So things like water harvesting and microbiome, and leveraging that biology to reduce the costs and equipment, right? Even if we can use hydroponics, we still have to import in the processed chemicals, which rely heavily on a fossil fuel-based production system. And I do have an idea to a small startup to develop multiple revenue streams to support this and to dovetail this research back so we can improve and regenerate life here on Earth. So using that regenerative approach, we can improve areas like pollution and radiation management. We can also explore other areas such as closed loop systems for damaged or degraded environments, or new environments that we don't currently take advantage of, such as underground, and increase yield in our overall soil health. So all of that leads to the question, how do we go from the left on the moon to something on the right? And so when I've talked to many people, they say, oh, the moon's dead. There's this feeling that the moon is something other. And I'm here to say that I would say the moon is not dead yet. It's dead, not yet alive. The rock, the regolith we see on the moon is basalt, or in the case of highlands, we have plagioclase feldspar, olivine pyroxene. These are all rock types that we see on Earth. And in fact, the tropical kind of volcanic picture we see here on the right is that exact same rock, right? So how do we go from the left to the right in a way that suits our timelines? And that's through this regenerative model. So here, there's two major types of rock on the moon: the highlands type, the kind of the whiter part that we see here on the top from the Apollo 16. And we also have the mare type. Well, when you look at the moons, the darker kind of grayish black part. These are the as I just had mentioned. And so people ask still, can we grow plants on the moon? And I say, yes, we can. So last year, University of Central Florida researchers published the growth of actual plants in real Apollo samples. We can see that at the bottom right. During the original Apollo days, in the top right, you can see radishes, I believe, that were exposed to lunar regolith and found otherwise safe and unaffected. They had it kind of sprinkled around them. The Chinese have launched a mission in Chang'e 4 where they successfully sprouted plants on the moon, and they grew upwards. So the lower gravity does not seem to bother at least that particular species. I believe that was cotton, but I may be wrong. And plant seeds have gone and returned to Earth, and they continue to grow, and their progeny continues to grow. And as others have mentioned, simulants, simulated material, represent a good test bed to develop this science when we're otherwise constrained with our sources. So there's a lot of challenges here. This is I'm not going to read through all of this, but this table compares soil to regolith and the consequences that plants might struggle with. This is an excerpt from a review paper I'm hoping to publish here in the near future. But we can see soil aggregation, water interaction, cation exchange, nutrient availability, organic matter, microbiome, fungi, pH, particle distribution. There's others as well. All of these play into whether or not a plant is going to be successful in soil and the basically lack thereof that we find in raw regolith. So, like some others here, I've been looking over the last 2 years or so, inspired in no small part through Space Ag, of changing this through biology. And I have built a team out of the University of Minnesota where we're looking at using earthworms to do this. So there's three major types. You have the epigic, that you kind of composting worms, the anisic, which dig down and up, and then the endogic, which kind of dig through the soil and harvest on the grains. So we've been conducting experiments here for a while, and been working to develop a successful worm habitat. Some of the findings we found is that regolith to manure ratio. So we've been using horse manure, as they are monogastrics and probably closest to humans in terms of manure. Water levels have to be carefully controlled. I think somebody else pointed to that when you have too much water, the material can quickly compact and hard pan. I have had it so that literally I've been stabbing it with a metal pick, and it kind of concretes. It eventually relaxes, but it's definitely something to monitor and control. The dry regolith itself, I found to be deadly to worms. So the mucus, it's very hydrophilic, and it will strip away any mucus on the worms, and they will desiccate and die. And then the recipe of mixing, at least for our experiments here in University of Minnesota, has required some tweaking, and it can greatly impact outcome. So here's some of the results. So we did night crawlers. These are common in fishing. Lumbricus terrestris, they're an anisic type, mixed with horse manure. These made it at least 11 days. I will point out that night crawlers, even in regular earth soil, have been difficult to culture. But we can see here, looking at the top, we can see the worms successfully infiltrating the mixture. And we can see at the bottom these very large soil aggregates. And it may or may not be obvious, but right in the middle, you can kind of see a tunnel down into it. That tunnel is coated with a very rich looking black organic matter, highly indicating some significant chemical and physical alterations happening within what I would now call soil through the earthworm burrows. Perhaps more promising, we have the red wiggler Anisa fetida types, the composting type worms. So this is an experiment been run over past while, and we can see, looking on the left, the kind of raw mixture very early on, day 5. I believe there are 4 worms in this dish, and you can still see that kind of whitish tint that you would expect from a Highlands type material. And then we can see through day 18, we see a lot of castings, a lot of soil aggregates, and by day 20, if I didn't tell you that that was lunar regolith, you probably wouldn't have known, right? So this is a very fast and significant process that we're seeing here, and our experimental data is validating our theses that we've been testing. Oh, we've also done mare. So on the left, we just can see this is a 24-hour experiment. We have the raw mare organic matter mixture, and on the right, we have a 24 hours with worms. And we can already always see soil aggregates. We can see changing. We can see the infiltration of the worms through the material. And so we can very quickly kind of determine what's happening. And not only is this important for the moon, but it's important to understand on the Earth because I forget the exact number, but it's generally believed that earthworms transform every bit of non-desert or non-tundra piece of soil in the world in an average of 7 to 10 years, right? And we have evidence to suggest that earthworms are actually responsible for something like 60 or 70% of changes in soil. And so by leveraging earthworms and other microbes and other soil organisms, I believe we can overcome these challenges with life, right? So we don't need chemicals. Nature, life will find a way, right? So this is a similar version of the chart I showed earlier, but instead of the regolith and soils, on the right, we can see the tactical efforts that my review paper and my team here is exploring to overcome and test and validate these changes. So I know I'm a little over, but our upcoming work, we're working on physical and chemical characterization, significant more replicate testings for statistical significance. We have plant growth trials under the way. We have bioinformatic analysis already occurring. We're looking at pre-processing the material, right? So those are things we can do to improve the outcome and the habitability for worms. And we're working on an automated facility construction. And we have evidence, right? So Suzuki et al. Has shown that worms will physically alter particles, for example, and Carpenter et al. Has shown that worms can alter chemically weather things like feldspar. So a lot of promising research here and experimental validation already undergoing. And then longer term, we're hoping for maybe some orbital experimentation. I will say one area of need is for human waste composting. That will be a challenge, but not currently one that we're focusing on. So just disclaimer, I do have some intellectual property pending on this. So systems and methods offer farming and systems and methods for authors, medicine and health as part of a larger portfolio of 8 patents already granted and another 6 pending. I do have aspirations to turn this into a business, but right now it's a research team. So I just want to shout out to the professors and other students here at University of Minnesota that are contributing to this work. And just thank you all. Feel free to email me. Sounds like there's a lot of people I'd be happy to collaborate with. And then I do have a small website, not much there, for the Offer with Agriculture Company.